Hello everyone. So this is a pre-recorded presentation of our ANTS paper on the security of the MR-LWE problem. So this is joint work with Bootland and Frederik Vercauteren, and all three of us are working at Castryck, which is a research group at KU Leuven in Belgium. Now, what is this MR-LWE problem? Well, it's a variant of the LWE problem, which was formally introduced by Regev in 2005, and which soon became a very popular cryptographic building block. LWE stands for learning with errors and revolves around systems of linear equations over some finite prime field, say, where the modulus p should not be too small. But instead of considering exact linear equations, such as the ones depicted here on the slide, one considers noisy linear equations or perturbed linear equations, where to each of these constants ci some error, small error ei was added. And small here, this means that these errors were sampled from some narrow distribution centered around 0. And this also explains why the modulus p cannot be too small, because inside fp it should be meaningful to talk about small elements. So let's call these perturbed coefficients b1 up to bm, and so one obtains an approximate linear system of equations. So now the LWE problem is the following. Given such an approximate linear system of equations, find the solution S1 up to Sn. In other words, find the Si for which all these equations are indeed approximately satisfied. So in order for this to be a well-defined problem, one needs to have more equations than unknowns, or alternatively, one could impose extra conditions on the SIs. For instance, a popular assumption is that the SIs are small themselves, and then a square system might be enough. Now, how about solving this problem? So it might be tempting to think about Gaussian elimination as an option, but when performing row reduction, all these implicit errors, they start combining with each other, they start combining with these coefficient aij, and then soon everything becomes indistinguishable from uniform. So this is really a no-go, and actually we do not know how to solve the LWE problem efficiently. That's of course the main reason why we are interested in it from a cryptographic point of view. Maybe one way to feel that this really is a difficult problem is by noticing that you can view LWE as an instance of the bounded distance decoding problem, which is a famous problem in lattice geometry. So this is with respect to a certain lattice. And what is that lattice? Well, in order to see that, let's rewrite our linear system of equations in a matrix form. And now the lattice consists of all integral vectors whose reduction modulo p. If you use that as the right-hand side of our linear system of equations, then the linear system becomes solvable in an exact manner. So all these integral vectors having that property, they form a lattice. And clearly any integral vector reducing to the original ci's modulo p belongs to the lattice, because then we recover our original linear system of equations before we started perturbing it. But we are given this perturbed system, so we are given some point, but not belonging to the lattice, but lying close to it. So if we can solve bounded distance decoding, we recover the Ci, and then we can proceed using Gaussian elimination. So that's the connection between LWE and bounded distance decoding. Now, why is LWE so popular in cryptography? Well, it has proven to be a very flexible and very versatile problem to build on. So you can tweak it in all sorts of ways, and also it very naturally leads to key exchange schemes or encryption schemes, but one can also use it to build signatures. It's also famous for constructions in homomorphic encryption and so on. At the same time, it has really nice security guarantees. Maybe one of the more famous statements is this random self-reducibility, which means basically that the average instance of the LWE problem is as hard as the worst case, the worst instance of the LWE problem. And that's really nice because in cryptography, typically one relies on some average form of a problem. At the same time, quantum computers are not known to help. So altogether, this means that LWE is a popular building block for building crypto systems that are supposed to remain secure in a post-quantum era. And so it's not a coincidence that when you look at the NIST competition on post-quantum cryptography, of the 26 second-round contenders, 9 schemes are based on some form of learning with errors. And it's almost certain that at least one or two of these schemes will eventually be declared as winners. But a big disadvantage of LWE is the key size. So to hide this secret S1 up to Sn, okay, so which consists of n elements of Fp, you need this entire linear system. And remember, we want to have more equations than unknowns, so it's at least a quadratic amount of data that you need to hide this secret. Now, the most popular way of reducing the public key size is formalized in what is called RLWE, or ring learning with errors. So this was introduced by Lubashevsky, Peigert, and Regev in 2012. And the rough idea is the following. So consider the matrix corresponding to our linear part. And remember, we mentioned that we have more equations than unknowns. So maybe think for simplicity of a system with 2n equations and n unknowns, and then you have 2 square blocks on top of each other, say. And now we are concentrating on one of these blocks, and we are going to replace that by a structured matrix. For instance, as a typical example, but actually a bad example, as I will say, as we will see in a second, circulant matrices, so matrices that are obtained from its first column by cyclically shifting the coordinates. And so clearly, to remember such a matrix, it suffices to store the first column. And interestingly, this matrix can be viewed as a matrix of multiplication by the polynomial having this first column as its coordinates inside the ring fpx modulo x to the n minus 1. And that's with respect to the basis 1x, x squared, and so on. And so this working modulo x to the n minus 1 really causes this circulant behavior. Okay, and so our ring LWE sample, if you want, can be rewritten as in polynomial form as follows. So this polynomial a of x, this corresponds to this matrix multiplication, and then our secret can be encoded as a polynomial, and our constants can be encoded as polynomials as well. So these constants are perturbed again, so it's an exact polynomial plus some error polynomial. So the coefficients of this e of x are our noisy components e, I. And then the big question is, of course, does this affect the security? Okay, so now we are working with structured lattices, if you want. Can this structure be exploited? So here's something which is a concern. Let's call it the evaluation attack, and it was analyzed in detail by Eisenträger, Halgren, and Wouter in 2014. So using that 1 as a root of this polynomial x to the n minus 1, one can see that evaluation at 1 is a well-defined homomorphism from fpx modulo x to the n minus 1 to fp. So let's see what this does to a ring LWE sample. Well, we have our sample, a of x times s of x is approximately b of x, so let's rewrite it in exact form. And so let's subtract this unknown noise again, rearrange terms, so e of x equals b of x minus a of x times s of x, and now we apply this ring homomorphism, so we evaluate at 1 to obtain the identity e of 1 equals b of 1 minus a of 1 times s of 1. And the crucial thing here is that this e of 1, which is just the sum of the coefficients of e of x, so it's the sum of these noise components, this is still small. It's a sum of n small terms, and so typically this is still small enough for what I'm going to say next. So think of that as small. And now using this equation, one already can make some guesses for s of 1. S of 1 should be such that the identity b of 1 minus a of 1 times s of 1 is small. And so if you are given a number of such samples, then typically this determines s of 1 uniquely, and so this leaks s of 1. It's not devastating, it doesn't leak the entire secret, but it's something you don't want. Now, I have to stress that this attack does actually not apply to ring LWE when instantiated properly. Okay, so the actual definition by Lubashevsky, Peigert, and Regev is technical, so I won't go into the details here, but it naturally excludes to work modulo polynomials of the form x to the n minus 1. And actually, the most popular and easiest proper instantiation of ring LWE is to work modulo the polynomial x to the n plus 1, but also where this n is itself a power of 2. And so this x to the n plus 1 then is a 2-power cyclotomic polynomial. So let's stick to those polynomials from now on. And now we introduce the MRLWE problem from the title. So this was introduced actually by Pedroso, Ulua, Troncoso, Pastoriza, and Perez Gonzalez in 2015. MRLWE stands for multivariate ring learning with errors. And the idea is just the same. As before, we replace all these square blocks by matrices of multiplication. So we also do that here. But now we work with matrices of multiplication inside a certain quotient of a multivariate polynomial ring. So the most concrete and most important proposal is to work in fp xy modulo x to the n1 plus 1 and y to the n2 plus 1, where these n1 and n2 are again these powers of 2. So we are working modulo these 2 power cyclotomic polynomials again. And so we are working with matrices of multiplication with respect to the basis, consisting of all monomials that have degree smaller than n1 in x and smaller than n2 in y. So this is the most natural basis you can choose. Yeah? And then the samples look as follows. Okay, so let's write this as a of xy. So this comes from our multiplication matrix times our secret s of xy equals c of xy, but now we perturb with this error polynomial. Let's call it e of xy, and this sum is as before called b, so b of xy in this case. Why did Pedroso, Ulloa, Troncoso, Pastoriza, and Perez-Gonzalez consider this? Well, it's not just for the sake of generalization. For them, it was a natural choice in the application they had in mind. So the application had in mind was in homomorphic encryption, and more precisely in homomorphic signal processing. And so for them, for this, they had to work with matrices or even higher order tensors. And so it was natural to use like ciphertext spaces of the above form. Okay. Now, the main observation over the current paper is that multivariate ring learning with errors falls prey to the evaluation attack that we just mentioned, but in a rather dramatic way. By the way, this was also observed by Cheon, Kim, and Yi in a paper also studying signal processing in the homomorphic context. So why does it fall prey to the evaluation attack? Well, let's maybe write this quotient in 2 steps. So first consider fpx modulo x to the n1 plus 1, and now consider polynomials over that modulo y to the n2 plus 2. We are going to assume that n2 is a divisor of n1. Remember that both n1 and n2 are powers of 2, so we definitely have that one is a divisor of the other, and so without loss of generality, by exchanging the role of x and y if needed, you can assume that n2 is a divisor of n1. And then indeed you see that x to the n1 divided by n2 is a root of this polynomial y to the n2 plus 1. Because if we raise x to the n1 divided by n2 to the power n2, you find x to the power n1, which in our ring, or our coefficient ring, is indeed minus 1. As wanted. So we can build a ring homomorphism from this, from our ring to a smaller ring, namely this coefficient ring, fpx modulo x to the n1 plus 1. And the homomorphism is just substituting x to the n1 divided by n2 for y. And we can play the previous game. So we have our sample. Let's write it in exact form. Let's rearrange terms. And now let's apply this ring homomorphism. And the crucial thing to observe is that this thing that comes from the error polynomial, so if you do this substitution in the error polynomial, and we end up with an element of this ring fpx modulo x to the n1 plus 1, if we write it to the basis 1x, x squared, and so on, we find a polynomial with small coefficients. Okay, so it's important here that we work modulo this y to the n2 plus 1 for this to happen. So this has a nice wrapping around behavior, and that's also where these minus signs that I didn't specify come from. In any case, so this is a polynomial with small coefficients. And so this last equality, e of x comma x to the n1 divided by n2 equals b, and so on, this can be read as an RLWE sample, but in this much smaller ring fpx modulo x to the n1 plus 1. And so solving ring LWE, maybe given a few such samples, in this lower dimension leaks the evaluation of s at x and x to the n1 divided by n2. But the thing is that it doesn't stop there. So we had this x to the n1 divided by n2 as a root, but every odd power of that is also a root, just for the very same reason. And actually this gives us n2 different roots of y to the n2 plus 1, so we have complete factorization. And for each of these roots, we can play the previous game. So by solving n2 instances of ring LWE in dimension n1, we obtain all these evaluations. And then it's easy linear algebra. Probably we will go into more details on that in the live part to build the entire secret from that. So this is more devastating than in the case of evaluation at 1. There we only leaked S of 1, but here we really leak the entire secret. So that's our main observation. So let's maybe apply this to some concrete parameters. So for instance, you had the following parameter set from the paper of Pedroso Olua et al. To work with n1 equals n2 equals 2 to the 7, so 128. They work modulo the next prime of 2 to the power 42, and they use for their errors a standard deviation of 1. And so then they expected that this would reach a security level, a massive security level of 2,500, so 2 to the 2,500 steps to solve it. But with this evaluation attack, you can reduce this to security level of 32 bits, so 2 to the 32 steps, and so it's easy to run this in practice. And Carl has implemented this in Sage, and so this really works perfectly in practice. Okay. So here's a brief slide on maybe a more high-level viewpoint on what's going on here. So basically what Pedroso Olua et al. Did was they considered ring LWE coming from tensor products. So this is another way of viewing this quotient of this multivariate polynomial ring, namely as the reduction mod p of this ring, z adjoint zeta 2 and 1, tensor z adjoint zeta 2 and 2. Yeah, and then they conjectured that the rank of that ring determined the difficulty of ring LWE, but clearly the problem here is that the compositum of these two rings is much smaller. So we clearly exploited the fact that zeta 2 and 2 is actually contained in z adjoint zeta 2 and 1. Okay, and so the compositum is much smaller. And so from this viewing point, you can generalize our attack from well, 2 components to any number of components, but also to more general rings, so rings of integers of more general Galois extensions, say. And so we have a reasoning in our paper that applies in full generality. However, we have this sentence here, good error growth, so that's something which is harder to control. I mentioned that working modulo y to the n2 plus 1 caused some good behavior of this error polynomial. We had just these signs. In general, this might be worse, so that's not entirely obvious that it will always work. So I would like to end with an alternative viewpoint on a multivariate ring learning with errors problem, which can also serve as a warning for users of the module learning with errors problem. So what is module learning with errors? This was introduced by Langlois and Stellet in 2015 as an interpolation between learning with errors and ring learning with errors. And the idea is to do like a blockwise ring learning with errors. So remember, in ring learning with errors, the whole matrix was replaced by a matrix of multiplication. In MLWE, you do this blockwise, and each block now corresponds, or each block is a matrix of multiplication by some different element, but always from the same ring fpx modulo x to the n plus 1, where n is now smaller, of course. So alternatively, you can look at this matrix as like so. So A11 of x now is the element by which the top left block multiplies, and so on. And so you can view this matrix as a linear transformation of a module over fpx modulo x to the n plus 1. So let's call the rank of that module m. So why would we like to look at such a thing? Well, being between LWE and ring LWE, it's a little bit more conservative than ring LWE, while it can still keep many of its advantages, but also it can be a bit more flexible. So in ring LWE, if you just restrict to 2 power cyclotomics like we usually do, the ranks of your rings jump from 256 to 512 to 1024 to 2048 and so on. So if you'd like to do something in between, then module LWE can be helpful. For instance, in Kyber 768, which is a submission to the NIST competition, they work with a rank 3 module over fpx modulo x to the 256 plus 1. Okay, and so the rank there is 256 times 3 is 768, and that would be impossible using 2 power cyclotomics in a purely ring LWE setting. Now imagine you would come up with the idea of speeding up module LWE again by endowing this module with a ring structure and replacing this matrix with a matrix of multiplication. But endowing this module with a ring structure basically amounts to considering things of this form, right? you consider polynomials and you mod out. And so in that sense, you just hit the multivariate ring LWE problem. And so we already seen that this comes with quite some dangers. Okay. Now, I have to say that, for instance, in the case of Kyber 768, where the rank of the module is 3, well, there you cannot use a 2-power cyclotomic polynomial to give it a ring structure, so you will necessarily have to use something else, and there you will not run into the troubles that we discussed in this presentation, because 2, 5, 6, and 3 are co-prime. But for instance, for m equals 4, then there's really something to watch out for. I will stop here.